In this problem, we have a straight wire that has a uniformly distributed charge on it sitting on top of a table, and we'd like to calculate the electric field at a point above the middle point of the straight wire. This problem is identical to example 10, where we're calculating the net electric field due to a line of charge. In the example, the line of charge was vertical. And if you rotate the picture, if you rotate the coordinate frame like I did in this picture, you obtain exactly the situation described in problem 50, which is this problem. So we're going to use the result from example 10, which is the electric field due to a uniformly distributed line of charge at a point at a certain distance x from the middle point of the center of the linear charge distribution. So the result is right here. Here's the result. Here's the formula that we are going to use to solve this problem. I'm realizing that I forgot to put the unit vector here. So the electric field is vertical, it's pointing up away from the straight wire. The straight wire has positive charge on it, so the electric field should be pointing away. Remember the components, the sideways components cancel, only the perpendicular components survive. That's from problem 10, sorry, example 10. And the result is an electric field pointing in the perpendicular direction away from the line of charge. So the electric field vector is going to be equal to the magnitude that we see here in the formula times j hat. We are going to substitute the numerical values to calculate the value of the electric field. So 1 over 4 pi epsilon 0, that's the same thing as Coulomb's constant K. Capital Q is the total charge on the wire, which is not given, but the charge density, linear charge density lambda is given. If we multiply lambda by the length of the wire, that gives us the total charge on the wire, so which is what I'm calculating here. But what is A? Well, in the original problem, the wire extends from negative A to positive A, so the length of the wire so A is equal to length of the wire divided by 2. So that's what I'm calculating here in the first line. So first I'm calculating the value of A, that's half of the length of the wire. So the length of the wire is 8.5 centimeters. A is then equal to 4.25 centimeters, or 4.25 times 10 to negative power of 2, 10 to power negative 2 meters. And then I calculate the total charge on the wire, which is lambda times the length of the wire, lambda being the linear charge density, which is given in the problem. So that's 2a times lambda, 2a being again 2.50 centimeters. So I'm multiplying the 2, and here I'm getting the total charge on the wire, capital Q. What is x? X is the distance between the middle point of the wire and point P. That is also given. X is equal to 6 centimeters. In other words, x is equal to 6 times 10 to the power negative 2 meters. So we have all the values that we need. We just plug in the values and calculate the electric field at point P. Here I have plugged in all the numerical values. If you go ahead and calculate this, here's what you get. 3.04 times 10 to the 4th newtons per coulomb I hat. Note that I have corrected my unit vector. The electric field is pointing up, By habit, I put j hat for that, but in my picture, in my coordinate frame, x-axis is pointing up, so the direction pointing up, the unit vector that should go, that should be pointing up is I hat, the one that goes with the x-axis. So I hat is the correct unit vector in this case. In part B, we bend this wire and turn it into a ring, and we calculate again the electric field at the same point P, 6 centimeters above the center of our ring. This is exactly what we have in example 9. Again, we have to rotate our coordinate frame such that the x-axis is pointing up and the y-axis is horizontal, but otherwise it's the same problem. So we will directly use the result from example 9. The electric field due to a ring at a point at a certain distance from the center of the ring, perpendicular along the perpendicular direction to the plane of the ring. And here's the result of example 9. Again, 1 over 4 pi epsilon 0, that's constant, that's equal to the Coulomb's constant K. Capital Q is the total charge on the ring, which we already calculated in part A. X is the distance between point P and the center of the ring. A is the radius of the ring, so we have to recalculate A because A is different now. Now here's how you can calculate it. I'm going to call the length, the total length of the ring, capital L. So L is going to be equal to, because we're bending a straight wire into a ring shape, the total length of the wire is going to be equal to the circumference of our ring. So capital L is equal to 2 pi A. And I'm looking for A because that's what I need to plug in into my formula. A is equal to L divided by 2 pi. If you plug in the value 8.5 centimeters for L, here's what you get for A. So just divide 8.5 times 10 to the power negative 2 meters divided by 2 pi. You get the value 1.35 times 10 to the power negative 2 meters for A. Now we have all the values. We can go ahead and plug in the numerical values to calculate the magnitude of the electric field vector E at point P. Here we have substituted the numerical values, and if you calculate this number, here's what you get. 3.45 times 10 to the 4th Newton per Coulomb I hat in the positive x direction, in other words, upward, based on my coordinate frame in the picture. Now, let's quickly compare the two values. In part A, we got 3.04 times 10 to the 4th, so this is slightly larger. When we bend the wire into a ring shape, we get a slightly larger electric field. Does it make sense? If you think about it, on average, the electric charge gets closer to point P when you bend it into a ring. So it makes sense that we get a slightly stronger electric field value at point P when we have the ring shape instead of the straight wire.